Yeah, okay, great. Hi, everyone. Thank you very much for being here for this talk about data protection in machine learning-based applications. And I'll start with the observation that the increasing deployment of machine learning introduces a dangerous double standard in the way we protect data. So what do I mean by that? Let's illustrate this double standard by taking a messaging application as an example. So in a modern messaging application, you probably have a database that will store the users, their messages, and a ton of relevant metadata like clicks or likes. And this database is continuously growing as users interact with the application. And the core logic for the application will be implemented with traditional code that interacts with the data to record and display users' messages. And this code will probably be exposed through APIs, maybe to third parties. Maybe part of it will run on users' devices for speed. But still, you do not expect everyone to have access to your messages. Why? Because every code will be mediated by some access control logic in the application, which ensures that the data is protected from users who don't have access to it. And this data protection and access control is a key concern in systems design. Now, if you look at the machine learning part of the application, we'll probably use some machine learning platforms such as Google's TFX or TensorFlow Extended to train models for different features of the application. So maybe we'll have some language model to do autocomplete while users type. We'll do some ad targeting. We'll want to recommend things to users. And we'll serve predictions through APIs and directly on users' devices as well, and also periodically retrain the models so that they can keep they can be up to date. So we'll use this growing database of the data we collect to periodically retrain and deploy them. And a key difference with traditional code is that those models and their predictions are not based only on data from one user, but on everyone's messages, likes, and clicks. And that's totally fine because machine learning only captures general trends from the data, so we are safe. No, not at all, actually. So in practice, machine learning also captures specific information about individual entries in the data set. So we've seen work showing that language models can reveal text snippets from the training data, including secrets such as social security numbers or credit card numbers. It's been shown that models' predictions are enough to infer with high accuracy whether a given data record was in a training set of a machine learning algorithm. And we've seen that recommendation models may leak information about specific behavior of a user to their friends. So how can we build into machine learning applications the same level of control over data that we have in traditional code? Well, we at least know of a good starting point. We can use a technique called differential privacy on the machine learning algorithms to bound the leakage, the privacy leakage of the training set data through those models. And this will work if the attacker only gets access to one model. But in practice, we are computing many different models over and over again over this growing database. And the models use both new data, but also reuse the old data that's in the database. So across releases of many versions of many models, the privacy loss through those models will add up, such that globally, the privacy guarantee will become meaningless. And while there are plenty of differential privacy machine learning algorithms, there is no system that can manage workloads of such machine learning algorithms to enforce a global guarantee of differential privacy over the entire lifetime of the application. So, can we make differential privacy practical for such machine learning applications? Well, as a step towards answering this question, we've built Sage, which is a differentially private machine learning platform. And it assumes access to machine learning training algorithms that can enforce a parameterized differential privacy guarantee, and it uses that as a primitive to enforce a rigorous global differential privacy guarantee across all models ever released from this growing database over the entire lifetime of the application. And in addition to enforcing this strong privacy guarantee, we designed mechanisms to mitigate two of differential privacy's practical challenges, which are significant roadblocks to adoption, and those are the running out of privacy budget challenge and the privacy utility trade-off. So in the rest of the talk, I'll give a short background on differential privacy, describe the two challenges in more detail, show how we overcome them in Sage, and then show an evaluation. So let's start with some differential privacy background. So at a high level, the idea of differential privacy is that you have a database with sensitive data, such as, for instance, a data set of drug purchases, and you want to allow an analyst to query this database to discover trends, such as epidemics, for instance, but without exposing the details of individual participants in that database. And differential privacy was the first and remains the only rigorous definition of privacy for this kind of use cases. And the way privacy is defined in this case is essentially as a stability constraint on computations that run on the database. And it requires that no single observation in the database has a significant influence on the result of that computation. So from a privacy perspective, intuitively, because no observation can change the output a lot just by itself, if someone looks at the result, they can't infer too much about single records in the database. And this is how this stability constraint is formalized. Essentially, what this formula says is that to achieve differential privacy, you have to add randomness to the computation to enforce the following invariant here in red, which is that for any pair, any possible pair of input databases that differ by only one element, the probability distributions you get over possible outcomes doesn't change much whether you run the computation on one of the database or the other. And there are two parameters, epsilon and delta. The main one is epsilon and controls how much the distribution can change when you change only one record in the database. And this is interpreted as a privacy loss that you incur when running that computation on the data. And the differential privacy literature is pretty mature at this point, including in machine learning, where it's been used to prevent the attacks I gave as an example by adding noise during the model training to make the process differentially private. And there is like a differentially private training algorithm for like pretty much any model you can think of. But as I said in the intro, there's two main practical challenges to using differential privacy for machine learning applications. So the first such challenge is that most differential privacy work has focused on the fixed database model, in which for each model trained, you incur some privacy loss that accumulates. So if we use this model in machine learning applications, we train one model and incur some privacy loss, represented in red here, and then a second one and a third until we reach the threshold, the maximum threshold of privacy loss we are willing to incur in the protection guarantee we want to give. And at this point, what happens is that we just can't use the data anymore. So even though we keep collecting new data in that machine learning applications, we are done. We can't train new models. And that's the problem of running out of privacy budget. Now, the second challenge is about the effect of differential privacy on the training procedure. So as I said, when we make machine learning training differentially private, we add noise at the training time, and this noise degrades performance. So here I'm showing for two types of models, the result of training the model and testing it on a testing set, and it shows the loss, so lower is better. And the high-level point is that if you have a data set of a given size, if you want more privacy, you trade that off for more loss, so less performance. So this is the privacy utility trade-off. Cool, so let's see how we designed Sage to go around these challenges. So the key to go around these challenges was to realize that in machine learning applications, we are always collecting new data. So we are operating on this growing database. So how can we leverage that to avoid running out of privacy budget? Well, we just need to change the way we analyze the differential privacy guarantees in this machine learning platform by designing a new interaction model for differential privacy, which is the way we analyze the algorithms, which is better suited to machine learning workloads than this fixed data set model. So that's what we did. And the model we came up with that we call block composition has 4 main characteristics. So first, instead of having one big data set, we split it into blocks. And when we want to train models on the data, what we'll do is that we'll combine some blocks so that those models can have a training set of the size they need. And this is important because some models need way more data than others. And third, despite the fact that we choose those blocks and combine them to train models, when we train a model, we'll just account for the privacy loss on the models we selected and used to train. So here, model 1 creates some privacy loss for the first 2 blocks, and model 2 creates privacy loss for the first 4. And finally, when a new model arrives, what can happen is that the previous model can influence the privacy parameters that will be used by that model. It can influence the computations that it runs, which are like 2 properties that were studied before, but it can also influence the data blocks it chooses to train on, and it can even influence the data that was collected. So if you think about it, maybe model 1 was like a recommendation model. So if you change the model, it will serve different recommendations, so we'll collect different data, and so it could impact the future model 3 that will train on this data. And despite that, we still account for privacy loss only on the blocks that we chose to train model 3. And what we show in the paper is that in this model, the global privacy loss that we incur over the whole growing database during the entire lifetime of the application is lower than the maximum privacy loss on any block that we used. Why is that important? Well, it basically means that as long as we stop using the blocks for which we reached the threshold of the global guarantee that we want, we are below that privacy loss. And because new blocks will never have been used for training, it means that they have incurred 0 privacy loss. So as long as enough new blocks arrive, we can keep training and keep releasing new models forever while keeping this fixed guarantee of differential privacy. Great, one challenge down. So let's look at the training part of the machine learning platform now. So now we're training models on subset of the data with noise to enforce differential privacy. So when releasing a model, how can we know that it will be good? Well, if you recall the privacy utility trade-off, if we don't do anything, the answer is like it won't be good. So what can we do about it? Well, if you recall, we can adaptively choose the blocks that a model trains on. So what we're going to do is start from the realization that if we give more data to a model, it actually becomes better despite differential privacy. So we'll do exactly that. We'll search for a good number of data points to give to that model. What does it mean in practice? It means that we'll train a model on a small amount of data with a small privacy budget, and we'll test it. And if it's not good enough, we retry on more data until it's good enough and we can release it. But now, we need to know how we are going to test whether the data is good enough. And we also, so for that, we can piggyback on typical machine learning pipelines that already have an evaluation step. But we need to make that step differentially private. And what happens when you do that is that the noise from differential privacy basically breaks the statistical properties of the test. So that's one more thing we need to account for. And we do that by accounting for the distribution of noise added by differential privacy in the test. And now we have a valid statistical test again. So this is the overall architecture of Sage, with the two key pieces being this access control part that enforces a global differential privacy over the lifetime of the system, and this iterative training part that retrains model until they are good enough to make sure that we only release good models. So now just a quick run through the evaluation. First, being able to combine these data blocks, which is one of the new points of our interaction models, is very important, because basically what it means is that we can end up with better models. So that's with Sage and without Sage, so we can end up with better models, and we also need less data to reach that model. And if we look at an end-to-end evaluation, what we see is that thanks to the new block composition of Sage, on the same stream of data, we can release way more model than we could with traditional differential privacy. So to summarize, the differential privacy literature has focused a lot on single algorithms running on static databases, but machine learning workloads operate on growing databases where models always incorporate new data and reuse old data. So Sage is the first system to adapt differential privacy theory to that growing database setup. And I think it opens really nice challenges, such as how to design good privacy allocation mechanisms that the systems community is really well positioned to address. So on that note, I'll end my talk and take questions. Thanks.
Questions?
Yes?
Hi, John Osterhout from Stanford, back here at Mike 4. So as someone who's basically an ignoramus on the main issues you're talking about, I was surprised to hear you treat privacy as a continuous quantity rather than a discrete quantity, and that it can be somehow gradually dribbled away in little units. Because I would think either somebody knows my credit card company or they don't, or they know about my drug habit or they don't. Can you give it, and in that sense, it doesn't seem like if the first thing that analyzes the data can't discover my secret thing, why would the second or the third one? Can you give an intuitive explanation for why it makes sense to treat it as this continuous quantity rather than a discrete thing?
Yeah, that's a great question. So basically, a good way to think about it is that you can treat privacy as the power you give to an attacker to ask a question about the data set that they're not seeing. And you can formalize that as a statistical test of, for instance, membership inference. So if someone wants to know if you were in the training set, they can run a test from the output of the models or any differentially private query to ask whether it's more likely or not that you're in the data set. And what you can show is that differential privacy bounds the power of such tests. So basically what it says is that the higher your privacy loss, the more likely is such a test to succeed. So in a sense, it's a continuous quantity, because you can still release more results and be less and less private, and this guarantee will degrade gracefully until a point where an attacker is very likely to be able to say, to answer questions such as whether you were in the data set or not. And basically, this quantity is the probability of failure of the test. So you say, oh, if they try to infer something from someone in the data set, they have a very high probability of failure. But if you release more and more differentially private results, this probability of failure will decrease until they can run a very good attack, basically.
Hello, Mihai Budiu from VMI Research. It looks to me like when you have a growing database, usually it will happen because you keep appending records from the same users.
Yes.
So a user won't have one record in the database.
Yes.
He will protect any one record, but he won't protect any one user.
Yeah, so that's a great question. So the theory we developed actually applies to the case where you want to protect the data from an entire user. But the problem is that now your database is only growing in the number of users, and it's very impractical to run a lot of analysis that we want to run on that. So the trade-off we chose to take for this work is to say that we'll protect only individual entries from the data set. So, but it does mean that someone could infer a lot from an entire user if they contribute a lot of data to the system. And yeah, we're clearly like not super happy about that, but that's at this point, it's like what we could solve, and I hope in the future we can tackle the harder challenge.
Let's thank the speaker again, everyone.